Let's talk bromine. So we're going to add bromine to double bonds now. Instead of using acids, we're going to switch to Br2, which is it reacts more or less the same. It's just that, well, you'll see. All right, so let's take an alkene and just react it with Br2. This will be a bromination reaction. So let's take I don't know, let's, not like that. Let's take a simple, I don't know, we'll do a 5-membered ring. Plus Br2. Now, it won't surprise you to learn that what we're going to end up doing, we're going to make 2 new sigma bonds, of course, because this is an addition reaction. And those 2 new sigma bonds are going to be both to bromine. So I'm going to draw in some stereochemistry here, and we'll do the general mechanism first, and then we'll worry about the stereochemistry. But of course, we're going to add 2 carbon-bromine sigma bonds. And we're going to notice that the stereochemistry is opposite, or anti. Right? So we call this an anti-addition. That doesn't mean that we're against addition reactions, although if you've watched all these videos right in a row, you might be starting to feel anti-addition. But in this case, what it means is it tells us what the stereochemistry is of the groups that we're adding. So in this case, stereochemistry, anytime we do a bromination, will always be opposite. So you have one bromine coming out at you, right, and one going back away from you. Right? But they're attached to different carbons, right? Notice that we have one on this carbon and one on this other carbon. All right, so how does this happen? So Br2, we're not going to think about it like that. We're going to think about it like this. And so Br2 is actually almost like HBr in that if we break this bromine-bromine bond, we can create a stable conjugate base, Br minus. And so that's what's going to happen is we're going to have this double bond come out, attack this bromine, and break the bromine-bromine bond. Okay. Now that's all well and good, except that what that's going to do, of course, is generate a carbocation. We don't really want to generate a carbocation in this case, and so instead, I'm going to draw this in brackets because this doesn't ever actually exist. So please don't, you don't have to draw this when this happens, right? Because what's going to happen is this bromine has these lone pairs, and so this lone pair is going to feed back in and add to the other carbon here. So this doesn't really exist, but we can think about it that way because what we get is we get a 3-membered ring with a bromine where that bromine is positively charged, right? So this bromine has given up one of its lone pairs. It now has 2 lone pairs and 2 bonds. So this bromine has a formal charge of +1. Now notice that I've drawn the stereochemistry here because it's a 3-membered ring, the stereochemistry has to be, these two have to both be wedged or both be dashed. You could also draw dashed bonds if you so choose. Whoops. Right, so if you draw this is also correct. You could draw them both forward or you could draw them both back. It doesn't matter as long as you do that. This positive bromine is called a bromonium ion. Right? And this is, people have actually isolated compounds like this and shown that we actually do create this 3-membered ring. There are actually bonds between both carbons and the bromine, and we are able to create this positive bromine. Now, of course, this is an incredibly reactive compound, a positive charge on bromine. Bromine is not something that likes to have a lot of positive charge on it, and so you have a conjugate base floating around, you have your bromine there. So this is going to come in, attack this position, make a sigma bond, and break a sigma bond. So we're going to do a substitution reaction here where the second bromine, for lack of a better term, comes in and makes a sigma bond at this position and breaks it there. And now, every time this happens, the new bond that you're making from your second bromine ends up opposite where the other bromine was. And basically, this comes from having to break that sigma bond. So as the one bromine comes in, right, imagine the bromine is coming in from this direction. Here's my carbon. So here's my carbon, right? Carbon is the eraser. As this bromine comes in and makes a sigma bond to it, what's happening on the other side of that carbon is this bromine is, I don't have three hands, so I can't really do this. All right, we're gonna do it this way. Ooh, ooh, ooh. Can't do it. Okay, so bromine comes in, bromine goes out, but they're happening at the same time. I just don't have enough hands to demonstrate that, and I can't have this thing, I can't hold this thing up in any way. So we can figure this out. Here's here's my carbon atom, right? As this bromine comes in, this bromine, so we have a bromine already attached. As this bromine comes in, this bromine is pushed out, and they just replace each other. But in order for that to happen, they have to come from opposite sides, right? Because otherwise they'll run into each other as one is leaving and the other one is coming in. And so basically that's what it boils down to. That was the worst demonstration I've ever done of this kind of thing. In class, it's a much better demonstration, I promise. But yes, so you always get this anti-addition when this second bromine comes in to break the bromonium ion up. Okay? So uh, always get anti-addition. So now we have stereochemistry, of course, to worry about when we do these additions, because sometimes if we use Br2, we'll always get this anti-addition. Right? Now in this case, we just use bromine, so we end up with two bromines, so it doesn't really matter which position we attack, right? I could have this bromine attack this other position, and I would get the enantiomer of this compound. Right? So we could get, if I had the bromine attack the other position, we would get a bromine here and a bromine here, right? Still anti, but we've switched the wedge of the dash. So this is, you always get anti-addition, but we get two enantiomers. Right? So when we draw this, we don't draw both enantiomers. Don't draw both enantiomers. We assume both are present. Right? So you only have to draw one of these, and it's assumed that the other one will show up. Right? So another instance of organic chemists just being lazy and being like, yeah, there's another compound in there, but we're not going to draw it. We're just going to assume that it's there. Okay. All right. So the bromohydrin reaction is in the bromination reaction's close cousin. So this is bromination. I probably should have labeled that. I've lost my marker. Here we go. This is bromination. The bromohydrin reaction is what happens when we do this in the presence of water. Oh my goodness, I'm just, that demo threw me off. All right, the bromohydrin reaction. So let's say that we'll do a similar thing, only I'm going to add one more methyl group, and the reason will become clear. And this time we're doing bromine and water. First things first, we're going to make the bromonium ion in the same way, right? Double bond attacks the bromine comes back in and attacks the carbon. So we get this. And now we have Br minus, but we also have H2O. And so this is where you would look at which of these is a more stable base, which of these is more reactive. It turns out that Br minus, if you look at the pKa's of HBr versus H3O plus, it turns out that H2O is actually the more reactive conjugate base. And plus, there's more of it around because you're running the reaction in water. And so what's going to happen is this water is going to come in and open the bromonium ion. So we made a bromonium, but now our nucleophile for our base is H2O, right? So if we run the reaction in water, the water takes over the reactivity from the Br minus. So H2O is going to come in, it's going to attack this position and kick out the bromine. Okay, we're going to break open the bromoniums. So once again, we're making a sigma bond and breaking a sigma bond. Now, a couple of things. First of all, you'll notice that H2O is attacking the more substituted position, right? We have a tertiary position here. We have a secondary position here, right? This will always be true. Attacks the more substituted position. And this should look familiar to you because this is basically just Markovnikov's rule. Right? Markovnikov's rule says that our conjugate base, or our base in these reactions, attacks the more substituted position. That's exactly what happens here. So the other thing is that this is still a bromonium. So once again, oh, I'm pulling out the demonstration again, right? Once again, as our water comes in from this side, our bromine gets kicked out on this side, right? Such a great demo. I love it. I'm going to do it this way from now on. As water comes in, bromine gets kicked out. So they have to be on opposite sides. So if the bromine is a wedged bond, that means the water has to come in and become a dashed bond. So when we do that, we're going to get the bromine over here is still wedged because that bond hasn't been broken or anything. Our water is going to be a dashed bond, and that because that water is dashed, that means that the methyl group now has to be a wedged bond. So basically the methyl group kind of moves out of the way of the water as the water comes in. So the water comes in from the back, the methyl group gets pushed to the front, and the bromine bond just gets broken, right? And we get this. The important thing is that the new bonds, CO and CBr, are anti to each other. Right? So then we lose H plus and we get to our final product. Minus H plus off the H2O, and what we have is OH, CH3, Br. Right? So the OH and the bromine will always be opposite each other. It's an anti-addition, right? Just like the previous one was, because we go through this bromonium ion. Right? So whenever we go through the bromonium ion, we always get anti-addition. That's really the take-home message here. So those are two new addition reactions. We have bromination and bromohydrin. They're very similar. The only difference is the presence of water. If water is present, water will be the conjugate base that comes in and attacks our bromonium ion. If water is not there, then we have to use the Br minus as our conjugate base. Okay.